All right, today we're going to jump back to 2014, to a really groundbreaking paper that basically changed how computers see the world. We're going to deconstruct the story of how AI learned to see not just a static picture, but an action, a story, unfolding over time. So let's start with the big puzzle here. By 2014, AI was getting really good at looking at a photo and saying that's a cat or that's a car. But a video is so much more than just a bunch of photos, right? It has time, it has motion. So how in the world do you teach a machine the difference between a person just standing there and that same person jumping for joy? That's a huge leap. And this slide, wow, it just lays out the core challenge perfectly. Image recognition is all about asking, what is in this picture? But video classification has to ask a much deeper question. What is happening here? And that doesn't just depend on what things look like. It depends on how they move. It's the difference between seeing a baseball and understanding the act of throwing a baseball. So to crack this problem, the researchers knew they needed two key ingredients. First, they needed a mind-boggling amount of video data for the AI to learn from. And second, they needed a totally new kind of AI architecture, one that could actually process the flow of time itself. Okay, let's dig into that first part, the data. You know, before you can teach an AI anything, you have to give it a giant textbook to study. The thing is, for video analysis, a textbook on this scale, it just didn't exist, so they had to create it. So what they do? They built one from scratch. The team put together this brand new dataset called Sports 1M, and it contained, get this, 1 million videos from YouTube. This thing was a training ground for AI on a scale nobody had ever even attempted before for video. And I mean, the scale here is just wild. 487 different sports categories, including 23 different kinds of billiards. But here's the real kicker. The data was weakly annotated. That's a fancy way of saying the labels came from YouTube tags, not a person carefully labeling every second. So a video tagged soccer could have crowd shots, interviews, whatever. The AI had to be smart enough to sift through all that noise and find the actual game. All right, so they've got this huge, messy library of videos. Now for the really big question. How do you actually build a brain, a neural network, that can see time passing? This is where their experiment got really interesting. Okay, first things first, you always need a baseline, right? A control group. For them, this was the single frame model. Now, this is a powerful AI for recognizing images, but it's completely blind to time. It would look at a single frame of a diver in midair, or a single frame of a basketball player's shoe, but it had no way to connect the dots between those moments to see the actual dive or the jump. But then you have the cool stuff, the experimental models. And one of the most clever was the slow fusion idea. Instead of looking at frames one by one, it looks at chunks of time. As information moves through the network's layers, data from different moments in time gets gradually fused together. This lets the AI slowly build this really rich, contextual picture of what's actually happening. So they unleashed these different models on that giant 1 million video dataset. I mean, this was a massive amount of number crunching. Everyone was betting that the fancy models that could see motion would blow the simple, motion-blind model out of the water. But what they found was, well, it was not what anyone expected. Yeah, the results were, frankly, a bit of a shocker. The new models crushed the old methods, no surprise there. But the real showdown was between the simple model that couldn't see motion and the sophisticated one that could. The simple one scored 59.3% accuracy, the complex one, 60.9%. All that extra work, all that complexity, for a tiny improvement. And this chart really drives home that surprise. All that incredible complex architecture to understand time only gave them a 1.6% boost. What this seemed to be saying was that to figure out what's going on in a video, what things look like, the appearance, was way more important than how they move. Now, this discovery, while super interesting, created a whole new practical problem. Training these enormous models was taking forever and costing a fortune. So to keep making progress, they needed to find a way to speed things up, and that led to a really clever, biologically inspired trick. I mean, you have to remember, the reality here is that training these things was just painfully slow and super expensive. We're talking weeks of computation. They absolutely needed a shortcut, a way to make it faster without throwing away all their progress. And their solution was so elegant. They basically copied the human eye. Think about how you see. You have your direct, focused vision, your fovea, where everything is sharp and high-res. Then you have your peripheral vision for the bigger picture. So they built an AI with two streams. A fovea stream that saw the center of the video in high detail, and a context stream that saw the whole scene in low res. And you know what? This two-stream trick worked like a charm. By not wasting computer power on rendering every single pixel in high res, they cut down the workload dramatically. The result? They got a 2 to 4 times speed up in training time. And, get this, they lost almost zero accuracy. It was a huge win. But here's the thing. The real legacy of this paper, the part that really changed the game, wasn't just about teaching an AI to know the difference between bowling and billiards. It was what they discovered next, when they started asking, okay, what else can this thing do? And this is really the million-dollar question, isn't it? They'd built this AI that was an expert on sports. Was that all it was good for? Could this incredible knowledge base they'd created be repurposed to learn something totally new, something completely unrelated? And the answer was just spectacular. They took a totally different, much smaller dataset with actions like applying eye makeup or playing the flute. When they tried to train an AI from scratch on this small dataset, it basically failed, only got about 41% accuracy. But when they took their big Sports 1M model and just fine-tuned it, its performance shot through the roof to over 65%. This idea is called transfer learning, and it was a game changer. And you know, the researchers themselves summed it up perfectly in the paper. What the model learned wasn't just how to see a football. It learned something much more fundamental about the physics and patterns of the visual world. It learned how to see, and that knowledge could be applied anywhere. So, in the end, this incredible paper helped prove something fundamental about AI. The ultimate goal isn't just to build one AI that's good at one thing. It's about building these foundational chunks of knowledge that we can then pass on, transfer to new AIs so they don't have to start from zero every single time. It really makes you wonder, right? What are these Sports 1M datasets of today? What foundational knowledge are we building right now that's going to be the textbook for the AI breakthroughs of tomorrow?